In this video, I'm going to prove what's called the difference identity for cosine. Once we've seen that, I probably won't prove every single identity formula. Might do one or two here or there as we go through. There are going to be quite a few of them. But I kind of want to show you what another kind of proof looks like. Remember that I'm going to ask you to do all of your proofs the way I showed you in the previous video. Start with the left-hand side or the right-hand side, depending on which is more complex. Recopy the left-hand side, and then manipulate each step until you get to the right-hand side. Get it looking in the form of the other side. That's how I'm going to want you to do your proofs for this class. It's a formulaic approach. You're always going to do the same thing, so you don't have to think too much about it. But there are different ways of doing proofs, and so I want you to see a few different ones. The formula for what we call the difference formula for cosine is the difference between two angles. The cosine of that difference is equal to the cosine of alpha times the cosine of beta plus the sine of alpha times the sine of beta. That's the formula. Alpha and beta are two angles. For our demonstration here, we're going to call this one here alpha. So that's slightly larger than, I think I'll write that in a different place. That's slightly larger than a 90-degree angle is alpha. So this here is alpha. And the angle from here to the origin to Q is beta. This small angle here is beta. The difference between these two angles is alpha minus beta. But notice that it is itself an angle. So alpha minus beta is an angle, and I can take the cosine of that angle. That's what that part means. Now I've made a copy of this circle. I'm going to drag that over here so you can see it is actually just a copy, and I'm going to change a few things. Now, as it turns out, my software won't let me erase anything on the copy. So this copy is going to stay, well, as it is. But I can make some changes to the original. So I'm going to change Q, I'm going to change P, and in fact, what I'm going to do is rotate this angle around so that this line segment here is sitting on the x-axis. In other words, I'm going to take this angle and I'm going to put it into standard position. And there it is. I've just rotated it. But the points have to be different because they have different coordinates. So I've renamed those as well. Let's make the observation that since this is angle angle alpha, and it terminates at point P has the coordinates cosine alpha, comma, sine alpha. Similarly, point Q is going to have the coordinates cosine beta, sine beta. In my new diagram, well, in the original diagram that I changed, this angle has measurement alpha minus beta. Remember back here we said that this is alpha, this is beta. When you take the difference of those two, you still end up with an angle. This angle is just this angle here, is just this angle rotated. So it has the same measurement, alpha minus beta. That's its size, alpha minus beta. So the coordinates of point A are going to be cosine of alpha minus beta, sine of alpha minus beta. The coordinates of B are 1, 0 because we rotated this angle so that it would be in standard position. So we know the coordinates of that point. I didn't mention, I probably should have, that these are unit circles, right? So if this wasn't a unit circle, this would be whatever the radius is. But since I've started out with the assumption, I didn't express it to you, but I started out with the assumption that these were unit circles. Now we're going to find the distance from P to Q and the distance from A to B. And because these angles are the same size, these distances will also be the same. Using the distance formula, let me remind you what that is. The distance between any 2 points is equal to the square root of the x-coordinate of the first point minus the x-coordinate of the second point squared plus the y-coordinate of the first point minus the y-coordinate of the second point squared. Now, the coordinates of the points that we're interested in the first case are P and Q. So the coordinates are cosine alpha, sine alpha, and cosine beta, sine beta. So the x-coordinate of my first point is cosine alpha, and the x-coordinate of my second point is cosine beta. That's what's going to go here and here. The y-coordinate of my first point is sine alpha, and the y-coordinate of my second point is sine beta. So I'm going to use those details, if you will, to fill in this formula. I'm going to write it down here because I don't have a heck of a lot of space. The square root of, I'll make that as long as I need to when I get there. The coordinate, x-coordinate of my first point minus the x-coordinate of my second point, that difference squared, plus the y-coordinate of my first point minus the y-coordinate of my second point, that difference squared, and I want the square root of that whole thing. If I expand this, I'm going to get the square root of, really rather a long expression, so I hope I can squeeze this in here. Let's see, I'm going to have cosine squared of alpha minus 2 cosine alpha cosine beta plus cosine squared of beta plus sine squared alpha minus 2 sine alpha sine beta plus sine beta squared. That's all under the square root, and I've had to break the line here because I didn't have room. But now I can reorder these. I'm going to start back here. This is equal to the square root of cosine squared alpha plus sine squared alpha. So I've just moved changed the order. I've taken this plus sine squared alpha here and moved it to right after the cosine squared alpha. I'm going to do the same thing with this cosine squared beta down here and this sine squared beta down here. I'm going to change the order. Let's put plus cosine squared beta plus sine squared beta next. And then what I have left is this minus 2 cosine cosine minus 2 sine sine. I'll put those in next. Minus 2 cosine alpha cosine beta. Sorry, I'm writing so small. Minus 2 sine alpha sine beta. And now I can make the observation that cosine squared alpha plus plus sine squared alpha is equal to 1. So let me use a highlighter. This, because of the Pythagorean identity, is equal to 1. And this is also equal to 1. Now these are different angles. Alpha and beta are different angles, right? But if I use the same angle in this expression, then the sum of the squares of the sine and the cosine of that angle is going to equal 1. So when I rewrite this again, this is going to be 1, and this is going to be 1. So let's see, where shall I write this? It's getting hard to do this. I'm going to need some space to do the same thing for the other circle. So let me play around with this just a little bit. All right, it turns out that I can move some of these things. This software is very funny. It lets me move things sometimes and not others, and sometimes it lets me move them. Where does this really go? I think it goes here. Sometimes it lets me move them on screen, but almost never. It almost always requires me to move. If I'm going to move anything, I have to move it on screen while you're watching. So I apologize for that, but we're getting there. Oh, good. Okay. So now I know that this overlays the circle that we're working with, but I've got a little bit more room here to finish the job. Okay. So where was I? This is going to be equal to the square root of 1 plus 1 minus 2 times the cosine of alpha times the cosine of beta minus 2 times the sine of alpha times the sine of beta. Now I can put that all in my square root. This, of course, is 2. So I'm going to cheat. Normally I don't like to do this, but I'm running out of room. So I'm going to change this in here to a 2 because the next step will be to factor a 2 out of everything. 2 times 1 minus cosine alpha cosine beta minus 2, oops, not 2, I'm factoring the 2 out, sine alpha sine beta. Okay, that's as far as I can take this. At the moment, this is what I have as being the distance between P and Q. I'll draw a little dotted line here between P and Q. And I'm going to call that D1. So this is my generic distance formula right here. But this distance formula is D1 because that's the distance between those 2 points. Now I'm going to do the same thing for these 2 points. Let's draw a dotted line there as well. And this one I'm going to call D2. The distance between these 2 points, the distance D2, is equal to the square root of, let me erase this axis a little bit. Okay, so I'm going to have the x-coordinate of my first point, which is cosine alpha minus beta, minus the x-coordinate of my second point, which is 1, that difference squared, plus the y-coordinate of my first point, which is sine alpha minus beta, minus the coordinate of my second point, which is 0. So it's just going to be this thing minus 0 squared, or just this thing, just that expression. Erase this. Oh, I can't erase that axis. Doggone it. Let me move it down a little bit. Can I move it down? Oh, sometimes I just have the hardest time with this software. There we go. Okay, now let's simplify that expression. This is going to be equal to square root of, I have basically here an a minus b all squared. So I'm going to have an a squared minus 2 times ab plus b squared. And that works out to cosine squared of alpha minus beta minus 2 times cosine of alpha minus beta plus 1 plus the sine, going a little skew with here, squared of alpha minus beta. That's still all under my square root there. Now, the angle alpha minus beta, this is an angle. So I can take the cosine of that angle and then I can square the result. So this cosine squared of alpha minus beta is just the cosine of an angle squared. And this is just the sine of an angle squared. And it's the same angle, the angle that measures alpha minus beta. So those two add up to 1. Cosine squared plus sine squared is 1. Minus 2 times the cosine of alpha minus beta plus 1 under the square root. And if I simplify that, I get 2 minus 2 cosine alpha minus beta, still under square root. Now that's simplified. It doesn't really look like I've made much progress here. I have this messy expression here. I can't do anything with it. It's simplified as much as I can. And the same thing can be said about this expression here. The thing is, they're equal to each other because I found this one by looking for the distance between these 2 points. And I found this one by looking for the distance between these 2 points. And these 2 distances are equal because we just rotated this angle to get this angle. So I can now set these 2 things equal to each other and continue my work. Unfortunately, in order to do that, I'm going to need to clear up some space. So this would be a good time, if you need more time to write notes, to pause the video, because after this sentence, I'm going to stop the video and I'm going to erase a few things. So not all of the information on the screen will continue to be available. All right, so I have erased what I can, and now I'm going to try moving some things. Like I said, sometimes the software will only let me move things while you're watching, basically. I don't know where to put this. It's too long really to put anywhere. I'll tell you what, let me let me write what I was, this was D1, and this was D2. Let me, instead of moving them, let me just copy the information. I want to say that these two things are equal to each other because this distance between these 2 points, this distance between these 2 points are equal. And this distance, using the distance formula, is D1, and that's what we found here. And this one was D2. So we can set these two expressions equal to each other and continue. Let's see what happens if I try to move the circle itself. Ah, yes, that's a bit helpful. The coordinates of P, there, we can keep that in place. There we go. The coordinates of Q can go there. And then let's see, maybe I'll erase some of this. Oh, I can't erase anything there. Okay, so what that gives me is a little bit of space to write the following. The square root of 2 minus 2 times the cosine of alpha minus beta is equal to the square root of, I'm going to have to write over my circle here, but I don't think there's really anything for it. 2 times 1 minus cosine alpha cosine beta minus sine alpha sine beta. Close parentheses, that's all under a square root. Now I'm going to square both sides. So I'm just going to end up removing the square roots. Equals. You know what? While I'm at it, again, to save space, I'm going to factor a 2 out of this. So I'm going to rewrite that. How do I want to do it? I guess I'll just start over. Factor a 2 out. I got 1 minus cosine of alpha minus beta. And here I have 2 times 1 minus the cosine of alpha cosine beta minus sine alpha sine beta. And I can divide both sides by 2, which gives me, I'm just going to make a note of it here. That gives me 1 minus the cosine of alpha minus beta equals 1 minus the cosine of alpha times the cosine of beta, forgot my s in here, minus the sine of alpha times the sine of beta. And I'm out of room again, so I'm going to erase this line here. This is actually where I started. I would like to have had this up here, and I can do that on this side, but I was really struggling to find a place to put this one. So basically, I just do that for now. It's very messy. This would be unacceptable. If you were to turn this on a challenge set, I would just say, I can't read this. This is unacceptable. But because I'm narrating, because I'm telling you where things are coming from, hopefully you'll accept that, well, you'll accept my messy work. So where am I? Well, let's try subtracting 1 from both sides. That gives me negative cosine of alpha minus beta equals, I've subtracted 1, I'm subtracting 1, negative cosine alpha cosine beta minus sine alpha sine, that should be a beta, sine beta, and then negate everything, multiply through by negative 1. Cosine alpha minus beta equals cosine alpha cosine beta, plus, because I multiplied the whole left-hand side and the whole right-hand side, right, by negative 1, that changes all the signs. So I have plus sine alpha sine beta. And this is the result I was asked to prove. So I have shown you through a series of steps of logic and algebra and identity work, most of which was the Pythagorean identity, that the two sides of this statement here are in fact equal, regardless of the sizes of angles A, or angles alpha and beta. As long as alpha and alpha are all the same, and beta and beta are all the same, this statement is always true. And that has taken me darn near 20 minutes, so we're not going to do a whole heck of a lot more of this type of work in this video. I will point out that this is one of the formulas you want to either memorize or put on your note card. I'm going to erase the screen now, and I'm going to write this at the top, and then I'm going to make a few other notes before we end this particular video. Okay, everything's gone except for our formula here. I think I'll put it here. And this is the result of a considerable amount of work. I will not expect you to reproduce this. I wanted you to see what it's like to prove an identity that's not quite so formulaic. But there are also other formulas, and we're not going to take the time to prove every single one of them. So this is what we call the difference formula for cosine. The sum formula for cosine is very similar. It is cosine of alpha plus beta equals the cosine of alpha times the cosine of beta minus the sine of alpha times the sine of beta. So for cosine, notice that you're taking the cosine of a sum of two angles. You have this information with a minus in between. If it's the difference of two angles, if this is a minus, this is a plus. The other side of the formula has a plus in it. So that's something to keep in mind. You'll want both of these on your note card or in your notes. By way of example of how it might be used, if you were asked to find, this is just example 1 from your textbook from this section, the cosine of 5 pi over 4 minus pi over 6. You could instead write this as the cosine of 5 pi over 4 times the cosine of pi over 6 plus the sine of 5 pi over 4 times the sine of pi over 6. Very quickly, very easily, we know that the sine of pi over 6 is a half. The cosine of pi over 6 is root 3 over 2. The sine of 5 pi over 4 uses the reference angle of pi over 4. It's in quadrant 3, so it's negative. Pi over 4 has a sine of 1 over the square root of 2, and it's negative. And cosine 5 pi also uses a reference angle of pi over 4, so cosine of pi over 4 is 1 over root 2. In quadrant 3, cosine is also negative, so we're going to have a negative there. That gives me negative root 3 over 2 root 2 minus 1 over 2 root 2. And that is negative 1 minus root 3 all over 2 root 2. And that's an exact value. So that's the kind of answer I want for problems like this. I don't want a decimal. Don't start putting decimals in up here and then adding them together to get down here. I want you to do the arithmetic. Your calculator will help with some of that, but I want to see exact answers. It has to be said that this kind of question doesn't really come up very often in so-called real life, right? But the use of this formula is very handy in various different other settings. So this type of problem sort of motivates why we might need to use this formula, why we might want to know this formula. But in fact, apart from a few exercises, you won't necessarily see problems like this. All right, that's all I'm going to do for this video. There are more examples and there are more formulas, but these are the two big takeaways that you need from this section are these two formulas. I used the wrong pen there, so give me a second. This formula here and this formula here. These are the first two identities that we're going to be using that are standard formulas that we need to know. So beyond the list of identities, fundamental identities that I talked about memorizing earlier, add these two to this list, all right? And we've got more to do, so hang in there.